Okay, I'm sending over the Git link in case you guys want to open it at any point. And I'm going to share my screen. So I chose to focus on antibiotic resistance. I think it's a cool topic because it's kind of pressing issue. And there were some cool data sets out there. For example, I used this one from the ECDC, the European Center for Disease Control. And they have data that they report for example, this is antibiotic consumption across Europe. So they are sort of tabulating it per country. I don't know if I can switch over. You can still see that, right? Yeah. The table, great. Yes. So they kind of reported this like downloadable table 2021 from years 2012 all the way to 2021. And it's like an Excel sheet, really, and it has all these different sheets. For example, this sheet is for beta-lactams, which is just a type of antibacterials. And this one is for another type of antibacterials, other beta-lactams. And it has these like funky codes, GO1C, GOEAC. And I discovered that they are classifying the antimicrobials by the WHO. So apparently WHO has its own way of classifying drugs. It'll have they have 5 levels. And for example, this is the first level, which is the most intuitive to get, acquainted with. So this one is depending on how the drug is administered or absorbed. And for example, this is why all of the codes in this sheet start with a J, because over here on the first level, these are all anti-infectives. So I thought that was cool as well. But as you can see, for example, on the first sheet, they're talking about beta-lactams and how they're consumed in the community of all of these countries. And if you keep browsing, you go even all the way here, you see that now they're talking again about tetracyclines and these beta-lactams again, but now it's in the hospital sector. So they're kind of giving you not duplicates, but sheets that have counterparts, one for the community and one for the hospital sector. And that has to do with how the medicine was prescribed. So if you, for example, went to your pharmacist and you got it over the counter, that's community. If you went to your GP and you got a prescription, that's community. But if you had to be in a hospital, that's a hospital administration, right? So they have, for some medicines, most of them, they have both sheets. So it'll depend on how easy it is to identify if you're sick or if you have very common symptoms, whether you'll get a prescription that's within the community data set or whether you'll enter the hospital data set. Great. So they had their own sort of data dictionary. It was quite limited, but most of the data was quite evident from the way it was tabulated. And it was quite easy to read. But basically, the numbers that you will see in each cell are DDDs, like a dose per day. It's calculated as a maintenance dose. So it's just a quantity that's calculated per treatment per 1,000 people. So per 1,000 inhabitants of that country. And they also left some notes. For example, some of these sheets have a row called Finland, and then the other ones have Finland A, for example. Like for example here, so that when it has the A, they mean that they're counting the nursing homes and those, but it's not consistent across the whole. For example, here is just Finland. So I just made a call to delete Finland. And they also made a note that Luxembourg had changed their data acquisition past a certain year. So I also got rid of Luxembourg because that was not consistent across all the dates. So basically, if I ever refer to antimicrobial or antibiotics, I'm using them interchangeably. One is an umbrella term of the other, but I'm specifically focusing on bacterial infections and the medicines against those. Yeah. So this is a table, just as you upload it onto the Jupyter notebook. Obviously, I wanted to get rid of, we said Luxembourg and Finland A whenever, and all the Finlands actually, because it's not going to be consistent, and got rid of all the NaN values and these weird compound annual growth rate, and this artifact of, I think, the upload, I got also rid of those columns. So basically, once you get rid of everything, you don't have that much to go by. So these are all of the tables. I wish actually I could show you the cell codes because it was a few of them. So I would love to be able to show you some of the code here. So as you can see, I just uploaded them independently, the beta-lactams for community on one data frame, and for the hospital another data frame, the other categories, the macrolides, whatever, one for the community, and then a different one for the hospital. And then there are some things like these polymyxins that do not have a community counterpart, and we'll talk about it a little bit down below. I have some notes on that. But basically, after you clean all of these different guys, you are left with something like sort of, oh yeah, I also had to change Czechia to Czechoslovakia, not Czechoslovakia, but Czech Republic and Czechia also had to be like, you know, made into one consistent nomenclature. Let me see, after this is cleaned, yeah, we're finally here. So this is kind of like what it looks like. I decided to make a dictionary to get hold of all of these data frames together. So after I did that, I'm trying to see where's the next interesting bit of, yeah, perfect. So we have several medicines for which we have data in the community and data in the hospital. I left some information on them as well, but I don't want to read too much from this. But basically, it's not per se medicine, a specific medicine for a specific infection, but also how far along in the infection you are and how spread it is. So it's not easy to correlate one-to-one the type of infection to the type of prescription that you're going to get. However, these are basically the 5 main categories: the tetracyclines, the sulfonamides, macrolides, and beta-lactams that you have data for in the community and in the hospital setting. Cool. Now, for some of them, you only have data in the hospital setting. The polymyxins, no, not meant to do that. Okay, the carbapenems and the reserve antibiotics, which are sort of last resort. And these are only administered in the hospital setting because of different things. So the polymyxins and the reserve bits are because they're so toxic and they become so dangerous. So they're used as a last resort. While, for example, the carbapenems, they're only prescribed at the hospital level because they are susceptible to generating antimicrobial resistance. So antibiotic resistance, really, which is, you know, a cool thing. So they're being kind of like held back because they can generate resistance in when they're treated or when they're used loosely. So for example, I basically decided over here, if I have a drug and I have a data frame for the community and one for the hospital, to combine them. It just seemed that it was arbitrary and country by country how you access the prescription. Some countries, apparently in Greece, you can go over the counter to the pharmacy and get it. So then you for example, would be in the community table. But for most of the countries, you would need some blood work, for example, in order to get diagnosed and then prescribed. So some countries are more strict. And then it just seemed like, because the threshold was arbitrary, to just merge them and get a total value. So this is what I did for every medicine. I just added up both of these data frames, right? Some of these were not data typed correctly, so I fixed that. Good. And basically, I just did them for all of them. The ones that are only prescribed in the hospital setting, I left alone. And then I gathered all of them into another dictionary, basically. So all of the ones are combined and all of the ones that are hospital only. Cool. And now, thanks to Felipa, really cool suggestion. Basically, I had tons at this point, even though I've combined some of them. I have tons of these little data frames. So in order to be able to plot them and kind of gather them all into one single data frame so I could compare different drugs, I used Pandas Melt. So it's really cool function. I made this little graph, so hopefully it'll kind of illustrate what it does. But if you have one single data frame, it'll sort of elongate it and create several instances of the same year. So the year will be a repeat, but then it'll assign a new column title, whatever you give it. You have to set that for every iteration of Pandas Melt. You tell it the new title that you want in this column header, and then it will gather all of the variables from the column that you gave it. So pretty cool. It will just gather those values. So that was my strategy, to do that for all of them, and then basically use one of them as sort of the blueprint and attach the unique values from the others on, and generate sort of a big data frame that just went on as many medicines as I had. So I did that, and this is basically what you get. So country, the year is a repeat per value. And then for each of these sort of categories or medicines, I had a different column. So this really made my life a lot easier. So thank you. And then I decided to plot these. So per year, because we have so many dimensions here. We have the years, we have the countries, we have the drug type. I find it really awkward to use those 3D plots that you kind of swing around. So I just kind of did a slider for each year. So this is, if you look at the header, 2012, and then if we move it, 2013, 2014, blah, blah, blah. And what do each of these lines mean? So blue is the beta-lactam. So we can easily see that these are the most widely prescribed drugs. And it kind of makes sense because they're sort of like a first line of defense for people that have some common infections. Something very interesting here, I'm not sure if you can tell, depends on the color on your screens, is this like pistachio green, hospital reserve. They're supposed to be the last resort antibiotics, and look at Greece. I mean, I just found this absolutely insane. The last resort antibiotics are used quite loosely, it seemed, over there. This should be, in my opinion, a really tiny bar. Because situations like this are a perfect breeding ground for antibiotic resistance, to use these type of things loosely. So I thought that was interesting. So yeah, the beta-lactams are the most consumed. The hospital reserve category is the most consumed in Greece, kind of like a worrying level as well. And also, yeah, Sweden towards the end kind of spikes. I don't know if you're looking at that green pistachio bar. I'm going to go all the way back and just look at Sweden. And it's quite tiny, keeps kind of growing over time, really like small. And then after COVID, it kind of just shoots up. I'm not sure if it has to do with how we all kind of lost our immunity after COVID and then got sicker after. Could be. But what I decided to do was plot all of the antibiotic consumption together into one single column, like a total column here. And then doing a chloroplast. So I'm not sure if you guys saw this because I missed a couple of lessons, but this is like a cool type of graph. You know, when you see like an election night or something like that, and you put like a map and it has like color coded. So that's what it is. It has like a proper name, it's called chloroplast. And I did the same thing with a slider, but this is just representing the total consumption. So basically I'm going to slide it, and then the yellower it is, the more antibiotics are being consumed. The bluer it is, the less antibiotics are being consumed. So this is now playing. You can see this Greece just doesn't change. It's kind of just huge the whole time. And while Scandinavian countries remain quite low, and some other countries like Hungary are also quite low, Netherlands and some others are in the middle. And this is when I wish we didn't have so many non-values for these countries, because I want to really know whether this would have been a gradient or whether it truly is, you know, a spike in Greece and that's it, and it's a true outlier, or whether maybe the Balkan countries have a trend to overprescribe, perhaps overprescribe, I'm not sure, that's my hypothesis, antibiotics. So yeah, it didn't seem really like they had so many changes year to year, which was interesting. Actually, it's changed a little bit, but nothing major. Nothing flips from blue to yellow or vice versa. So that's interesting. Pretty stable. And now what I did is take the average from 2012 to 2021, kind of just take an average and standard deviation from that and do a violin plot. So you're seeing average across 10 years data. 10 years data, because it's 2012 inclusive. And you see every country has its own distribution, quite interesting. And Greece also has like a funny, very elongated distribution. This made me start to suspect that it was very thin. It made me think that perhaps their data acquisition was just very sort of accurate, that they perhaps had a way of gathering these instances of antibiotic prescription within very like fine buckets. Because I think if they had like a coarser method of acquiring data, they would have had like for example, something like this, where most of the data acquired falls into one bucket and not in the other. This makes me think that they have like tiny buckets, or that they have what's the word? It'll come to me, but it's susceptible to little changes. I started to think whether Greece was really bad, whether we should just isolate just hospital administration. So to see again whether Greece would still be an outlier, because if the hospital administration, I mean, it really looked like it from the pistachio bar in the other graph, that Greece was an outlier, but this would be a way to truly confirm that. So yeah, it has the widest spread of all. And again, it's very, very like narrow. And yeah, then I did some research, and it seems that because they were prescribing antibiotics over the counter so much over pharmacies, they started to restrict that in like 2020 or so. And they invested all this money in a new data acquisition system. So it has like they have a new Clio's mission: improve patient safety, blah, 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 blah. So it just, what's the word? Acquires data on the antibiotics that are prescribed. So monitors pediatric patients. So this is only for children, but I think it's making a huge difference because maybe this new system that they have in place is just allowing them to report accurately the data. And I even suspect that perhaps the rest of European countries are under reporting their data in comparison to Greece. Okay, so after this, I wanted to look up one specific category of medicine and bring in another data set of antibiotic resistance. So antibiotic resistance really is what I really cared about from the start. And I did some research, and I realized these carbapenems are especially susceptible to creating strains of bacteria that develop antibiotic resistance to them. So that is why, I don't know if you remember, but before they only had a hospital data set. They are not administered loosely. So it's widely researched in academia, and there's a ton of articles, and I just put a review here in case you guys want to click on it, I don't know. And then I found a different data set on Kaggle, antimicrobial resistance data, that pools, I don't know if I should, data from European countries for these different strains of bacteria, and identified among some of them, basically 3 of them, this one, that one, and that one, are the only ones that are known to be susceptible to antibiotic resistance. So if you treat them with the carbapenems over and over again, eventually they become resistant to them. And so I pulled them into, I just downloaded this data set where they just tell you the number of tests they run, the percentage that were positive, and then just the total that were positive for being resistant to antibiotics, and then a sheet for each of these 3 bacteria, the E. coli, the Klebsiella, and aeruginosa. And the numbers don't really matter because I ended up adding them all together. So I just pulled them and then kind of cleaned the data a little bit. And the thing is that they only have data from 2012 to 2015, which made me go back to my original data set and then chop that after 2015. But I guess it's okay. I just wish I had more relevant recent data. So for each country name, for each year, just collated the total number of resistant bacteria independent of the species. And basically, I pulled it as a column in my original big data frame. And then I just wanted to, basically, I'm just ending this by plotting these. So, well, this is quite fast. I didn't like that. Whatever. Let me pull that back. So in 2012, so there's a bubble per country and a color per country. So truly, if you can chase Greece over here, yep, you can see that it's still an outlier for resistance. So the resistance is plotted over in the y-axis. The amount of carbapenems prescribed are plotted on the x-axis, and the size of each of these corresponds to the total amount of antibiotics prescribed minus the carbapenems, just because I didn't want these two to be like codependent. So you can see that Greece is just an outlier. I think it's probably a convolution of things. Not over-reporting, but reporting perhaps more accurately than the rest of European countries. And also they do perhaps overprescribe the antibiotics, and they're generating a lot of antibiotic resistance. So this is truly kind of like worrying. If I was looking at this data, I would truly like strap on the amount. Maybe release some guidelines or something, because this is, I mean, this is crazy. This is really bad. So yeah, that's it. And just, you know, a general note, I've assumed that administering antibiotics directly is the only causation for generating antibiotic resistance, but like that's not true. A ton of things go into it, like agriculture and like how the land is treated and like what animals are fed and we eat them and all that stuff. So it's been quite reductive, but yeah, I just wanted to kind of follow a theory the whole way through. And that's it.